So I welcome you all and a very good morning to all of you. And before I go with our proceeding topic, in fact, we'll be talking about Hermitian Adjoint in this today's interaction, and then we will be talking about some of the important properties of these Hermitian operators, right? So that will be our target. It won't take much of time, but before we start our usual way of interaction, I would like to invite you to the auditorium, because in the auditorium we have some experts, and these experts are going to deliver some lectures on a very important application, especially for the students of India, and the app is called UA app. Now all you have to do is you have to register yourself in this app. Once you register yourself in this app, you will have a range of programs available online. I mean, all of those programs are skill-based programs. And the examples, like if somebody is interested to have some better skill knowledge on artificial intelligence, you can choose a course on artificial intelligence. And somebody is interested in Python, somebody is interested in some other kind of course, you can select that course and you can watch. You will be provided the respective videos in which you have chosen. Suppose you have chosen robotics, okay? You will get the videos of robotics. You will get those videos, and finally you have to be serious about those videos, because they will be taking examinations. You will be examined, and there's a lot of scholarship available in all these fields. And once you qualify that examination, you will get a certificate, and that certificate will make you eligible for a job, for a government job. So that's why this interaction is important. So I'm requesting all of you that at 2 o'clock we have that interaction in the auditorium, because they will take your attendance as well. You have to be present there, and I would like that all of you register in that UA app. So you register, and you can then later on decide yourself which direction you want to go, in addition to your usual academics. So today we'll proceed on our the quantum mechanical properties we have been talking about. In the last interaction we talked about eigenvalue equation, and now let's talk about a Hermitian adjoint. Now what's a Hermitian adjoint? Now if you have, suppose I have an operator, suppose I have an operator A. This operator A, if this operator A is equal to its Hermitian adjoint, and what's that? That is we also call it dagger, a plus-like sign. Okay, so if your operator is the reflection of itself, basically, if an operator is the reflection of itself in the Hilbert space, then we call it a Hermitian adjoint, right? And how we can suppose I have this operator. This is a Hermitian adjoint. It acts on some state psi, and this is equal to, say, some another state, because all of you know that when you act an operator on an eigenvector, what operator does basically, it transforms that vector into another vector, and it suppose it goes into a next state, say phi. Now, the condition is that if I write down a state psi a cap and phi, this, what does this mean? Now, if this A is a Hermitian adjoint operator, now suppose this operator acts on phi, you will get a result. And then this operator acts on psi, you will get the final result. And now if I exchange the action, if A acts on psi and then it acts on phi, the result will be same. The result will be same. So this is the very fundamental property of an Hermitian adjoint operator. So that means exchanging the kets and bras with respect to an Hermitian adjoint operator does not change the result. It doesn't change the result. Now the point is, what we have is, we have a very fundamental equation about the inner product. What is that? Suppose I have a vector zeta, I have a vector phi. This is always equal to, if I exchange it, this is phi, this is zeta star. Okay? This is a very important inner product that we have talked about in the past, right? And this will be used to verify some of the results. Now say for example, if I have an operator A and it has a power n, this is whole raised power, this is whole adjoint. And you can write down this as A adjoint raised power n. Okay, this is one of the properties. Another property is, suppose I have two operators, A operator, B operator, and I take its Hermitian adjoint, so I can separate out them A cap dagger plus B cap dagger, right? Okay, the next thing is, so this can lead to up to n. Suppose I have A operator plus B operator plus C operator, whole raised power, the Hermitian adjoint. This Hermitian adjoint will be given to the respective operators, A plus B plus C plus D. Is this clear? Right? Okay, there is another important operator, say, if I have A and B. Now, if I have the product of the two operators, and this is raised power dagger. Okay, now what this is equal to? Yeah? B dagger and A dagger. Now, let's try to prove this. Okay? Let's try to prove that A operator times B operator raised power, the dagger is equal to B dagger and A dagger. So for this, okay, what I have, suppose I have a state like this, psi A cap, B cap, and phi. Is this clear? And this will be equal to phi A cap, B cap, whole raised dagger, and then you will have psi. Is this clear? Right? Okay? So, how can we proceed from here? Now, if I define this B cap phi, B ket of phi, I will define another state in the same Hilbert space as the ket of zeta, right? And A I should write it, yeah, psi A cap is equal to the bra delta. Now you understand, see, if you have B cap ket of phi, if you take its bra, what will be that? Its bra will be, yeah, it will be bra phi B dagger. And for this you will have a bra. This is already bra, okay? Is this clear to you? So what I have done, I have defined the two parts, one as the ket of zeta and another as the bra of delta. Okay? Now I would like to take the inner product between these two. So we have to keep this equation in mind. Okay. Okay, so I might have to correct something later on, I don't know. So what I'll get here, when I take the product, here I will have the delta and zeta. And what is that equal to?
Zeta.
Yeah, that will be, for delta I have psi and then A cap. Okay, then for zeta I have B and phi. You check it. Okay? Now, can I talk about this? Delta and zeta is zeta. This is zeta delta star. I can say that, right? I can do that. So what should I write in the right hand side? For this ket of zeta, what will I write? Come on. Check it. Where is zeta? So for that I will write ket phi of B dagger. Okay? So you tell me, come on. So I'll write here ket of phi and B dagger. And for delta I will write
Psi of eta.
Yeah.
Psi
For come on. For zeta is gone, okay?
Delta.
For delta it is A psi, but what will be its opposite? It will be A dagger psi. So to make it ket, okay? So it will be A dagger and psi. Am I right? Should I write star here? The star is there? Fine. Now, if I take another star, what I have to do? If I take another star, the order will change. So the order will change. What I'll get here? I'll get here psi, B dagger, A dagger, and phi, star, and whole star. Am I right? Come on, can you compare this equation? The first equation that I wrote down. What was in the right hand side of that equation? What was in the right hand side of that equation? Yeah, what was that? That was psi, A cap, B cap, raise, dagger, and phi. Isn't it? Okay? Come on. What's happening? It's exhausted. Okay. Now, see, the order is psi and phi. In the last equation that I got, you check here, this is star and star. Star and star will cancel. Okay? What you are left with? You are left with psi, B dagger, and A dagger, and phi. So you are left with psi, B dagger, A dagger, and phi. Okay? You can see this equation. Everything is same. So if everything is same, then you can say that A cap, B cap, raised power dagger will lead us to B dagger and A dagger. Is this clear? Is this clear? Done? Okay, so you can generalize this equation for large numbers. Suppose I have A cap, B cap, and C cap raised power dagger. So what you'll have, you can write it as C dagger,
B.
then you'll have B dagger, and then you'll have A dagger. Is this clear? You got it? Clear? Okay. Okay, so can I move on?
Yes, sir.
Okay, right. So, now, there is another important property. See, when you have an operator which is Hermitian adjoint operator, or we call it simply as Hermitian operator, when it acts on a state vector, what happens? It gives you a number. And we say it's a number, it's a real number, right? And you get the same state vector. Now that's what we have to prove. We want to prove something like this. If I have an operator, a Hermitian operator, it's acting on the state zeta. From here, I'm getting lambda and zeta. Right? Now what I have to prove is, I have to prove that this lambda is not a complex number. It's a real number. Right? This is our target. So for that, what will I do? So what I have A zeta. So I will define here the bra of zeta. The bra of zeta. I define a state vector. It's a dual Hilbert space vector in the Hilbert space as the bra zeta, right? So if I define this vector, I would like to multiply this equation, right? If I multiply this equation with the bra of zeta, what I'll get? I will get zeta, then you will have A, then you will have zeta, then you will have zeta, and you will have lambda and zeta. Is this clear? It should be clear to everybody. Okay. Now, I have zeta and zeta, and this is equal to zeta star, isn't it? Right? So this we have as zeta A and zeta, isn't it? And what about this? I have, zeta, lambda, and zeta, then you have the star. Isn't it? Right? It's a pure algebraic way of doing mathematics over here. You can understand it, you can do it. So, now, what about this? This operator will act on zeta, it will give me lambda, right? So what will I get here? I'll get zeta, lambda, and zeta. This will be equal to zeta. Now this lambda, I have to take its complex conjugate. So I will get this out as lambda star, and inside I'll have zeta. The complex is gone. Right? I have taken the complex conjugate. So because on exchanging, I'm having the same state, zeta. So, what do you get here? You get here lambda and zeta is equal to lambda star, zeta and zeta. I can transfer this. I'll get lambda minus lambda star. And what is common? The common is zeta and zeta. And this is equal to 0. Right? Now what about zeta and zeta? The inner product between zeta and zeta. What is it? Yeah, these vectors are existing in your Hilbert space. And the necessary condition for the same kind of vectors in the Hilbert space is that they must be normalized. So in general, maybe there are cases where you will have a value other than that of 1, but one thing is for sure, that the value of this product is 1. So if this product is 1, so this product cannot be equal to 0, because either of the two has to be equal to 0. When you multiply one with another, you will get 0. So this is not 0. What is 0? Lambda minus lambda star is 0. So that means lambda is lambda star. What was lambda? Lambda was a real number. And it's telling you that lambda star is also a real number. So we understand from here that if you have a Hermitian operator, when it acts on an eigenstate, you get the same eigenstate, but in addition to that eigenstate, you have the eigenvalues. And the eigenvalues that you obtain, these eigenvalues are real numbers. Okay, so in the similar way, there is another important property of this Hermitian adjoint, and that is if you have a dagger of dagger, and this should give us A, right? Right? So, can you prove it now? Yeah. Come on. You have an operator A. Suppose it acts on zeta. It acts on the state zeta. And say you get a state phi. And if I define the bra, of psi, if I define the bra of phi, what will I get? And I'll multiply that bra of phi from left to this equation. What will I get? I'll get bra of psi a cap, and zeta is here. Then what I have? I have this is bra of psi and phi, isn't it? Right? But this psi and phi is equal to phi and psi. It's not zeta here. It is phi and psi star. Right? So what will I get here for this phi and psi? This is psi and phi. What I'll get? I'll get here phi. But for A, I will get a dagger. Am I right? I'll get a dagger. Now, and then I have my own psi. But there is a complex conjugate. Isn't it? Clear? So, now, if I change the order again, what's going to happen? See, I started with psi and phi. I wrote it in terms of phi and psi. Now, I want to write it back as psi and phi. What will I get? I'll get psi, a dagger, and its own dagger. Isn't it? And you will have phi. Star is there. Is it correct? So this star is gone because I have taken it 2 times. So if it's gone, I have the 2 equations now. I have the equation, I have the term, yeah, come on, you tell me now. Yeah, I have psi a gap
Zeta.
And what about here? It's zeta is equal to, yeah, come on. It's equal to psi, and you have a dagger, raised dagger, and zeta.
Phi.
Oh no, it has to be, so something is wrong. So here I have written it wrong. No, I have written a different vector over here, okay? Okay. Yes. Because I am talking about a Hermitian operator. So it has to be the same state. It has to be zeta. And then I define psi, and here it has to be zeta. You will correct it yourself. And you will have zeta in the final equation. Isn't it? Right? So you will have zeta. So what I will be getting finally is, this is psi, a dagger, zeta. This will be the case. Now, you can compare these two equations. The cats are same, the bras are same, so the operators in between must be same. That means a cap must be equal to a dagger raised power dagger. Is this clear? Maybe I committed some mistake. You can rectify it yourself, okay? So this is the way that you have to manipulate these vectors in order to obtain some of the important relations of Hermitian operators, right? There may be some additional identities that are existing. You will work out all of these. You will work out all of these equations, and the basic clue to prove any equation is that inner product. You remember the inner product? The inner product between zeta and psi is psi zeta star. That is the core. That's the core point that helps us to obtain these equations. Is this clear? Any questions? So I would like to stop here today. If anybody wants any kind of interaction, you can tell me, you can ask me. So you remember what I said in the beginning of this interaction. You will go into the auditorium at 2 o'clock. You will register yourself on your app, and believe me, that's going to be very useful for you if you are able to choose something that will suit your skills. All right? So you can